I'm Julian Shun. I'm a principal investigator in CSAIL and an assistant professor in the Electrical Engineering and Computer Science department at MIT. My area of research is parallel computing, and I want to talk about several of my projects in the area of parallel graph processing. First of all, what is a graph? A graph contains vertices and edges, where vertices model certain objects of interest, and edges model relationships between these objects. For example, you can use a graph to model a social network, where the vertices are people, and edges between vertices means that there's some relationship between the two people. There are many other applications of graphs. For example, they can be used to model transactions in financial networks. They can be used to represent distances between locations in transportation networks. They're also used in biology, neuroscience, and many other areas. And oftentimes there are many interesting questions that you might want to ask on these graphs. For example, you might be interested in finding a good cluster in a social network, or you might be interested in detecting fraudulent transactions in a financial network, or you might be interested in finding the shortest path from one location to another in a transportation network. And these are all questions that graph algorithms can answer. Today, graphs are becoming very large. They can contain up to billions or even trillions of vertices and edges, and therefore it's important to have high-performance parallel graph algorithms if we want to analyze these large graphs in a timely fashion. However, parallel graph algorithms are often very hard to implement, and therefore it's also important to come up with high-level programming frameworks that enable data scientists to more easily write their own parallel graph algorithms. And my research aims to design new parallel graph algorithms for fundamental problems on graphs, as well as design new programming frameworks to make it easier for others to write their own parallel graph programs. One of the main themes of my research is to look at both the practical aspects as well as the theoretical aspects of the solutions that I design. This is because not only do we want our solutions to run efficiently on the data sets we have access to today and on the machines that we have access to today, but we also want to prove strong theoretical guarantees on the performance so that we can ensure that they'll run efficiently even in other settings. For example, when we have larger data sets with possibly different properties in the future, or when we have machines with larger numbers of processing cores and deeper memory hierarchies in the future. Recently, we developed the Graph-Based Benchmark Suite, which is a collection of theoretically efficient and practical algorithms for over a dozen fundamental graph problems. And we were able to show that these algorithms can achieve both theoretical efficiency as well as practicality at the same time. We're also able to scale our algorithms to the largest publicly available graph, which is the Common Crawl graph with over 3.5 billion vertices and over 128 billion edges. We compared to the fastest existing solutions that reported results for the Common Crawl graph and found that our running times were faster. So here I'm showing the running times for two of the algorithms that we designed, K-core decomposition and connected components. And we can see that compared to existing solutions, our running times are better. Furthermore, the amount of hardware resources that we used to achieve these running times was significantly lower than the number of cores and amount of memory used by these existing solutions. I've also developed a framework for doing streaming graph processing. So streaming graph processing is important because many graphs are changing rapidly in real time, and we want to be able to run computations on these graphs while they're being updated at the same time. Existing streaming graph processing frameworks either use expensive snapshotting techniques or they separate the updates from the queries, which leads to high latency for either the updates or the queries. And to solve this problem, we designed the Aspen framework, which is a low latency streaming graph framework that can support updates and queries to the graph simultaneously. The key idea behind Aspen is a parallel compressed graph data structure based on persistent trees, which enables us to create lightweight and immutable snapshots of the graph efficiently. And queries can then run on their individual snapshots, and they don't have to worry about the graph being updated because the version of the graph that they're seeing is static. In Aspen, our graph is represented as a tree of trees, where we have a tree over the vertex identifiers, and each vertex has a tree representing its associated edges. And if we use persistent trees to represent our tree of trees, then this enables us to do updates efficiently via path copying. And in particular, when we update the graph, we only have to update the path in the tree that actually changed, and then the rest of the graph can be used by storing pointers into it. And also, each update will create a new root that is one of the snapshots that queries can use. And queries can always acquire the latest version of the graph by acquiring the root corresponding to the most recent update that happened in the graph. I also want to talk about the Graphit domain-specific language for graph processing that I've developed. Graphit contains an algorithm language to enable the program to specify the logic of a graph algorithm, as well as a scheduling language to allow the program to specify different combinations of optimizations to the algorithm. The algorithm language contains primitives for representing subsets of vertices or subsets of edges in the graph, as well as operators to apply computations over these subsets of vertices and edges. The scheduling language contains different optimizations that have been proposed in the literature for graph processing, including different traversal schemes, different parallelization schemes, data structure representations, different locality optimizations, as well as kernel fusion. So Graphit contains a compiler that can generate efficient low-level code from the high-level algorithm and scheduling specification. And because we separated the algorithm language from the scheduling language, this enables an easy exploration of a large optimization space just by tweaking some parameters in the scheduling specification, and the algorithm specification doesn't need to be modified at all. Graphit also has an auto-tuner that can automate the exploration of this large optimization space without requiring any manual tuning from the programmer. We compare the performance of Graphit to state-of-the-art graph processing frameworks on different data sets as well as different graph algorithms. And here I'm showing the slowdowns relative to the fastest implementation for each algorithm and data set combination. So a value of 1 means that it was the fastest, and a lower number is better. We can see that Graphit is able to achieve the best performance in most of these cases, and it's up to a factor of 4.8 times faster than the next fastest graph processing framework. And this is because Graphit's able to explore orders of magnitude more schedules than the existing graph processing frameworks. Further, by using a compiler-based approach, Graphit is able to easily apply global optimizations such as data structure transformation and kernel fusion, whereas these optimizations would require much more effort in existing graph processing frameworks. So here are some links to open source software and publications describing the graph projects. And we're always interested in learning more about applications of graphs in industry and applying our graph processing solutions to some of these applications.